Kia ora and welcome to the 2021 Level 2 Physics Mechanics paper. It's a whopping 6 credits, guys, so let's crack into this. Okay, so question 1, the ramp. The picture on the right shows a bike rider going over a ramp. The rider's speed at the top of the ramp is 10 meters per second. The angle between the ramp and the ground is 30 degrees. The top of the ramp above the ground is 1.1 meters. Show that the vertical velocity of the rider just as they leave the top of the ramp is 5 meters per second. Lovely of them to give us the answer. Let's prove this correct. Okay, so we're concerned with the vertical velocity just as they're leaving the ramp. So this essentially is like V, let me get my pen, V, I vertical. Okay, so to do this, we can split up our resultant, velocity into two components. It's always going to be made up of a horizontal component and a vertical component, okay? Anytime you get this velocity, never assume that this is a vertical or a horizontal velocity. This velocity is always split up into its vertical and horizontal. And we can use trig to actually figure that out. So let me redraw this triangle nicely over here. And so what we have is we've got our 10 meters per second, which is a resultant vector, and we've got our vertical component, our vertical velocity, and our horizontal. So let's label the triangle. So I've got hypotenuse, H for hypotenuse, which is our longest end. Then we've got O for opposite, which is going to be opposite the angle. Then we've got A for adjacent, which is in between the two angles, okay? So we've got our hypotenuse, that's a known value. We want to figure out our opposite, which is a vertical velocity. So what I have to pop in, what function do I use? Well, I have to use something that uses O and H, and that happens to be SO, O and H. SO is going to allow us to use our sine function, okay? And so sine theta equals O over H, okay? And so this is what we have to do. We have to substitute in the values that we know. So sine, pop the angle into the theta symbol, and then we are not sure what our opposite is, so leave it as an O, divided by 10, which is our hypotenuse. The next thing that we do is we have to get O, the opposite, all by itself. So I want to get rid of the 10. So to get rid of the 10, which is currently being divided by, I have to times it by 10, because the opposite of divide is times 10. So that cancels it out. That means I have to times 10 on the other side, and so I get 10 times sine 30 equals our opposite, which I've rewritten here, okay? So 10 times sine 30 is going to be giving our opposite, which is our vertical velocity. So plugging this into your calculator, you should get 5 meters per second. That's worth and achieved. All right, so let me just row out these diagrams. I'll redraw them soon. Calculate the maximum height that the rider will reach above the ground. Okay, so to make sense of that, we want to figure out what is the maximum height that this rider will reach. We don't know what that is. Let's figure it out. The first thing that you should do is you should always figure out what you have and what you don't have. So we want to figure out our maximum height, but what we do have is we've got our vertical velocity, okay? We've got our vertical velocity, which we've just calculated, and that is 5 meters per second. We've got a final velocity, which is 0. Why is the final velocity 0? Well, we're assuming that the final velocity is going to be at the top for this particular question, okay? We just want to find what's at the top. So our initial velocity is 5, and our final velocity up top is going to be 0, because everything at the top comes to a stop. The reason why is because all the forces are balanced, they're in equilibrium, okay? Okay, so our acceleration due to gravity is negative 9.8. Why have I made it negative 9.8? Well, my velocity, which is going up, I've defined that as a positive. My acceleration always acts down due to gravity, right? So because it's opposing the direction of my positive velocity, it is going to be defined as a negative, okay? So this is my acceleration, and it's going to be negative because it's opposing my velocity, which is going up, okay? So that's why I've made it negative. Okay, so I might as well tell you and explain further that if my velocity was going down, okay, it's going the same direction as gravity, okay? So both of them can be positive, okay, because they're going the same direction, all right? So, anyways, back to the question. D is what we're trying to figure out. So what equation on my resource sheet shall I use that uses all of these things? Yup, this one over here. So let's substitute in all my values that I know. So final velocity is 0 squared, and then my initial velocity is 5 squared. And then I'm adding this little package to this package, 2AD. So let me substitute in everything that I know. So I've got 2 times negative 9.8 times the distance, which I'll figure out soon. So to find out distance, I have to get it all by itself. I need to isolate it. So one by one, let's get rid of everything that is connected to D, okay? So the first thing I'm going to do is I'm actually going to simplify this equation a little bit. So simplifying 5 squared, that's going to be 25. Then I'm going to simplify 2 times negative 9.8, and that's negative 19.6. The reason why I didn't go 5 squared plus 2 times negative 9.8 is because these are their own little separate packages. This is its own package, and this is its own package, okay? So I keep them separate. All right, so to get rid of 25, which I want to get rid of everything outside of these brackets, you see. So to get rid of 25, this positive 25, the opposite of positive 25 is negative 25. So I'm minus 25 on this side, that means I'm minus 25 on this side of the equal sign. So 0 squared minus 25 is minus 25. So minus 25 equals negative 19.6 times D. To get D by itself, currently it's being times by negative 19.6. So to get rid of times negative 19.6, I have to divide this whole side by negative 19.6 because the opposite of times is divide. And so by doing that on this side, I have to do the same to the other side. And so D equals negative 25 divided by negative 19.6, and that gives me this value here. Okay, we've got a height from the ramp to be 1.2755 meters, but that's not what we want. We don't want the height from the ramp to the top. We want the height from the ground to the top. So what we'll have to do is we'll have to add this height over here to this height that we've calculated. So that's going to give us 1.1 plus 1 point, oh, that's meant to be a point over there. Let me just fix that. 1.2755. Remember not to round too early, team. And that should give you 2.38 meters, which is worth a merit. So if you got the distance in pink, that's achieved, pink for achieved, orange for merit, and there we are. Moving on to the next question. Okay. The diagram below shows a path of the rider when they leave the top of the ramp at 30 degrees, okay? 30 degrees. 40 degrees is what we want to find. So on the same diagram, without further calculation, sketch the path of the rider who leaves the top of the ramp at 40 degrees. So 40 degrees is going to be steeper, And so you might be tempted to draw a line that's like this. But that is not the case. Why is that not the case? Well, in level 2 physics, we always assume that there is no air resistance. So with no air resistance, actually, we are going to go higher, higher and further. Okay, so at a steeper angle, let me redraw that because that was at the same angle. At a steeper angle, we're going higher and further, okay? And you have to show that they're starting at the same point to get the merit. For a rider leaving the top of a 30-degree ramp at 10 meters per second, calculate the vertical speed of the rider when they land on the ground. Okay, so we want to work out the vertical speed just before they land on the ground over here, okay? And it's from the ramp, okay? Not from the ground, from the ramp. Okay, so what do? Let's figure out what we have and what we don't have. VF, which is the vertical velocity, the final vertical velocity down here, okay? This is our new final vertical velocity. Before we made the final vertical velocity up top, but now we want to work out this as the final vertical velocity. So let me just actually label VI vert and then VF vert. Okay, so here's what we have to do. Final vertical velocity, we don't know. Final initial velocity from the top of the ramp, which is here, is 5 meters per second. Acceleration is 9.8. Why is it 9.8? Well, I'm dealing with working out my final vertical velocity. And my final vertical velocity is going down, okay? It's going down. It's also, if we're comparing it with acceleration, which is also going down, they're going in the same direction. Acceleration is not opposing this velocity. So, because I've defined my downwards velocity as positive, okay, this is not, my acceleration is not opposing it. So it's also going to be positive, okay? So whatever direction my velocity is going in, I'm defining that as positive. Because it's going down, I've defined this downwards direction as positive. Acceleration is not opposing it, so it's also going to be positive. So that's why I have a positive 9.8. The distance is going to be 1.1 because I'm measuring it from its flight from the top of the ramp. Not the top of the flight, not from here, but from here. So this distance from the top of the ramp is 1.1, okay? So that's why my distance is 1.1. Okay, next thing. Based on all these values, the equation that I'm going to use is this because it's got the most values in it, okay? So by plugging everything in, we've got VF squared, which is unknown, equals 5 squared, which is our initial velocity, plus we've got 2 times 9.8 times 1.1, which is the distance. So I'm going to simplify things. So 5 squared is 25. And then in this bracket over here, we've got 2 times 9.8, and times 1.1, sorry, is 21.56. Now I can plus these together, and that gets me 46.56. That needs to be square rooted because we don't want velocity squared, we just want the final velocity. So to undo that square, we have to square root this side, and that means we have to square root this other side as well. So by popping this into your calculator, you should have gotten 6.82 meters per second. Alright, so this is worth and achieved. Calculate the horizontal distance travelled from the ramp to where the rider lands on the ground. Okay, so we want to work out how far this rider lands, okay? We want the horizontal velocity. We want the we don't want the horizontal velocity. We want the horizontal distance, okay? So whenever we're dealing with horizontal components or horizontal values or calculations, the equation that we use for horizontal things is always going to be this. The reason why we use this equation is because this is for constant velocities, and the horizontal velocity is always going to be constant throughout the flight because gravity does not act on the horizontal component. It only acts on the vertical. So we use this equation here. So let's use this equation to find out the horizontal distance traveled. What do we have and what do we not have? Whoa, seems like we don't have anything. So we're going to have to figure a few things out so that we could work out what the horizontal distance is. So let's start off by first working out the horizontal component of velocity. So again, remember, our resultant velocity is 10 meters per second from the ramp. We can split it up into its vertical and horizontal components. We've already figured out the vertical. We only want the horizontal component because we want to work out the horizontal distance. So using trigonometry, we are going to have to use our adjacent and our hypotenuse, okay? Because adjacent is our horizontal velocity. So what function will I have to use if I need to use my h and my a? Yep, it's going to be ka. So that's going to give us the cos function. So cos equals a over h. Substitute the values in. We don't know a, but we do know h, which is 10. I need to get a by itself. It's currently being divided by 10. What's the opposite of divide by 10? Times by 10. So I'm going to times by 10 on this side and times on 10 by this side. Timesing by 10 on this side cancels this 10 out, and we're left with a on its own. So a equals 10 times cos 30. So I've substituted that angle into the theta sign. Plugging this into my calculator, I get 8.66 meters per second. So that's my horizontal component of velocity. Okay, now that I've worked out the horizontal component of my velocity, now what I can do is, whoopsies, what am I doing here? Now what I can do is I can work out another part of this equation, okay? So I've got the horizontal velocity, let's work out time, because then we can rearrange to find distance. So remember, time, we cannot simply just work out time using this equation because we don't have enough things. So we have to use our vertical components to work out what the time is. The good thing about that is the time taken to go vertically up and down in projectile motion is the same time taken to go all the way across. Okay, so these two times can be equal to another. What equation am I going to use? I'm going to use this one here. So our final velocity is down here, okay? So our final velocity vector is going down. Let me change the color here. Our final velocity is going down. Okay, why isn't this working? Let me try that again. There we go. Okay, our final velocity is going down. Our initial velocity, okay, our initial velocity over here is going up. It's going up. Acceleration always goes down, okay? So, based on these vectors that I've just drawn, let's assign positive and negative signs, okay? So I'm going to make my vertical final velocity a negative as it's going down in this instance, and then my initial velocity is opposing that downwards direction, so I'm going to have that as a positive. Because acceleration is going down, it is not only opposing my initial velocity, it's going in the same direction as my vertical final velocity. So because my vertical final velocity is going down, and so is my acceleration, I want it to be the same sign, okay? So by doing that, I have a perfect equation to use with the correct symbols. So here I have my negative final velocity going down equals, by the way, I got this answer from up here, okay, equals my positive initial velocity from the ramp, which is 5, plus my negative 9.8, which is going down as well, times t. Okay, let's see what we can do here. We want to get t all by itself. So let's focus on getting rid of things. I'm going to get rid of the 5 because it's outside of the brackets. It's the easiest thing to get rid of at the moment. So the opposite of plus 5 is minus 5. So I'm minusing 5 from this side. That means I minus 5 on this side. So negative 6.82 minus 5 equals negative 11.82. What I have left on this side of the equal sign is my negative 9.8 times t. So to get rid of times negative 9.8, I divide this whole side by negative 9.8. That means I divide this whole side by negative 9.8. This cancels out. I'm left with t equals negative 11.82 divided by negative 9.8. Popping this into my calculator, I get 1.21 seconds. Okay, that is worth a merit. Okay. Next step, now that we've got our time and our horizontal velocity, we've got two things in our equation. So what we can do is we can rearrange to find our horizontal distance. Finally, we're there. Plugging in the values, 8.66 equals d over 1.21 times this side by 1.21 to get rid of this, times this side by 1.21. 8.66 times 1.21 equals a horizontal distance of 10.48 meters, and that is worth an excellence. All right, rolling into part 2. A rider rides around a circular bend with a radius of 7.0 meters at a constant speed of 10 meters per second. If the combined mass of the rider and the bike is 90 kgs, calculate the centripetal force required. So what do we have here? We've got the radius given to us over here. We've got the velocity of 10 meters per second. And we've also got the combined mass of the rider, which is 90 kgs. We want to figure out the centripetal force. According to your resource sheet, this is the equation that you should use. Substituting in all the values, you get this over here. Got the mass of 90 times the velocity of 10 squared over the radius of 7.0. And you should get this answer initially, but when rounding it to two significant figures, it is 1300 newtons. Don't forget the units. That's worth an achieved. When the rider is in the position below, they bike across a very slippery part of the track. Use physics principles to explain the path the rider takes when they bike across a very slippery part of the track. Show this path on the diagram with an arrow. Let's do it. Okay, so there's a slippery spill over here. What path is the biker going to take? Well, here's what I want you to know. The path is going to be tangent to this circular path, okay? So this is the new path that this biker is going to take instead of going all the way around, okay? Why is that the case? Let's have a look. Well, when the rider rides over the slippery patch, there is no friction between the tyre and the path anymore, okay? Since there is no friction between the tyre and the path, there is no more centripetal force acting towards the centre of the path, centre of this whole thing, okay? Remember, centripetal force is an unbalanced force, and when there is no unbalanced force which is allowing circular motion to happen, This means that the biker will continue to travel in a path that is tangent, okay, tangent to the circular path at a constant velocity, all right? And that's what I've explained here. This is worth a merit. Some trail bikes have a spring suspension system. The spring constant is 40,000 Newton per meters. A rider of a mass of 80 kgs sits on the bike, causing the spring to compress. Calculate how much energy is stored in the compressed spring. I like to always write what I've got. I've got the spring constant, which is K, and I've got the mass, which is 80 kgs. I have to calculate the energy stored in the compressed spring. So when looking at your resource sheet, what is an equation which works out energy and involves K, which is what we have been given so far? It seems like this equation over here, okay? E for energy. Okay, so to work out the energy stored in the spring, I need not only K, but I also need X, okay, which I don't have at the moment. So I can't use this equation just yet. What equation will allow me to work out X? Look at your formula sheet. It's this equation over here. So by figuring out what X is, then I can plug it into here and then work out what EP is. But I can't work out X because I actually don't have a force. I've got the K, but no force. So I'm going to have to work out force using another equation. What could that equation be? Well, one way to work out force is mass times acceleration. So I'm going to have to use this equation. So by working out force, I could plug it into here, rearrange this whole thing to find X, and then plug that X into this equation, and finally work out the energy stored. Okay, so it's a bit of a series of events here. So without a further ado, we've got F equals ma, got your mass, which is 80 times 9.8, which is a force of gravity. That equals 784 newtons. So getting one step correct in this whole process is worth and achieved. Okay, so now that I've got force, I could plug it into this equation here. So I've got 784 equals the spring constant, which is K, times X. Okay. Rearranging that, I need to get X on its own, so I have to get rid of the times 40,000. So to get rid of the times, I have to divide. So I've divided this side by 40,000. That means I have to divide this side by 40,000. So 784 divided by 40,000 will equal X. So by calculating this, I will get this, 0.0196 meters. That's the compression. X is the compression. So now by knowing what X is, I could finally use this to work out the energy. So I've got a half times K times X squared, and that equals this value here, rounding it to this many significant figures, 3 figures. I've got 7.68 joules, and that's my final answer with a merit. When a rider lands after a jump, they essentially have a collision with the ground. Use physics principles to explain fully how a suspension system makes a bike safer for landing. Okay, so whenever you get some sort of collision type question, you know that we'll be dealing with this equation here. So this is the momentum equals the force times change in time. Okay, so what is happening here? Well, before we delve into the answer, let's have a little bit of a think. What are the springs doing in the bike when they land? It's compressing, okay? The springs are compressing as the bike lands, okay? They're compressing as the bike lands. If we didn't have springs, imagine that bike wheel hitting the ground directly, okay? That's going to be pretty rough. The springs, as they compress, it's actually increasing the time taken for the bike to fully make impact with the ground. And so by increasing the time component, okay, you're actually decreasing the force of impact, okay? And that's because if this equation is rearranged, okay, we can rearrange to find force with momentum over time, okay? And as you can see, momentum is proportionate to force, okay? And so by increasing the time, you're decreasing the force of impact, and so that's going to be a lot safer for the bike, okay, for landing. Assuming that the change in momentum is the same, the spring suspension system increases the time of landing as the spring takes time to compress. By increasing the time, the force of impact decreases according to this equation here. Decreased force is safer for landing. So I've linked to the context and explained it thoroughly. All right, moving on. All right, we're up to question 3 now. Last part, we're almost there. Okay, so a rider and a bike with a combined mass of 85 kg climb 4 meters vertically in 3 seconds while biking up track. Calculate the average power required. So, you know me, I love to have all my values written out that I've been provided from the question. So I've got a mass of 85 kgs. kgs. My goodness, it's been a long day. Then I've got a time of 3 seconds and a distance of 4 meters. I have to find the power. If you look on your formula sheet, what is the equation for power that we have to use? It's this one here. Make sure you don't use a 1 for momentum with a little p. We want the power with a big P, okay? So this is the equation. How do we figure out power? It's work, W, over time. We only have time. We don't have work. So we're going to have to find out what work is so that we could find out what power is. What is an equation on your resource sheet that allows us to work out what work is? Yep, it's this right over here. Okay, so now that we've got this equation, surely we can work out work and then plug it in here. But we have an issue. We actually don't have a force. We have the distance, but we don't have a force to work out what work is. So we're going to have to work out what force is. How do I work out what force is? What equation shall I use? Yup, F equals ma. Let's start here, because it seems like we have mass and we know what acceleration is. It's always 9.8. Okay, plugging in those values, I get 833 newtons. Then I can plug this force value into here. So I get work equals 833 newtons times our distance. And I get 3332 joules. Okay, that's how much work is being done here. And work is a type of energy, which is why the units is joules. Getting this at least one step or this part correct is achieved. Now finally I could plug this into this equation here to work out what power is. So plugging in work over time, which is provided, I get a power of 1110.67 watts. That's the unit for power, and that's worth a merit. The biker rides over a 4 meter long bridge and stops 3 meters from the end. The bridge has a uniform mass of 700 kgs. The combined mass of the rider and the bike is 85 kgs. State the conditions required for the bridge to be in equilibrium. Okay, equilibrium means that there are no net forces acting. All the forces are balanced, okay? So, how do we write this? Well, I want you to consider that there are 2 types of forces acting, okay? There are torque forces and there are also just normal forces, okay? So, forces. There are no net forces, so this means all the upward forces must be equal to the downwards forces and therefore they're cancelling each other out. The next type of force is the torque force, which is a turning force. So there is no net torque, which means that anti-clockwise torques must be equal to the clockwise torques. Okay? Clockwise torques. So, next question. Draw labelled arrows to represent all the forces acting on the bridge. Okay, so I've given myself a clue just in case I myself may have forgotten. There are 4 vectors that we have to draw. So I've got the force coming off this rider, and it's going to be this downwards arrow. Then we've also got a uniform, because this bridge is uniformly distributed, we've got a central mass of the bridge, and that's this force acting right in the center of the bridge because it's the mass is uniformly distributed. We've also got these support forces over here which are acting upwards. Okay, make sure they're straight. Okay, so now calculate all the values of the forces acting on the bridge. So what are all the forces acting? We've got the force of this biker here, this rider I'm going to call it, and then we've got the force of this bridge acting downwards. Then we've got support force B, and we've got this support force A. Okay, we have to work out all of those forces, which I've made a table of over here. Okay, so how do we work out the force of the bridge? Well, remember, to work out force we have to use F equals MA. So here is how we do it. We've got the mass of the bridge, which is what? 700, which is provided in the question above. And then we've got 9.8, which is acceleration. And then putting that in my calculator, I get 6860 newtons. So that is the force of the bridge. Now I have to find the force of the rider. So the mass of the rider and the bike is 85 kgs, times that with 9.8, and then I get 833 newtons. Now I have to work out support force A over here. Okay, so support force A. If I'm trying to work out the force of A, I have to make B, support force B, my pivot point. Okay, so support force A, with B becoming my pivot point. This is a torque question, so we have to keep in mind that we're using this equation here. This is the torque equation where torque is the turning force, and it's the force of something, whether it's a rider or whatever, times the distance, okay, away from the pivot point. So remember, all anti-clockwise torques must be equal to the clockwise torques. So that's what I've written here as a reminder. Okay, so what are our clockwise torques? Clockwise, remember, goes in this direction, okay? Clockwise goes in this direction, the same way as a clock. Anti-clockwise goes in this direction, opposite to how a clock would run, okay? So, what are the forces? What are the anti-clockwise forces, okay? Well, I've already given you one. Support force A is going to go this way around this pivot point, okay? What about the rider? The rider, its force is going downwards, so if it were to keep twisting around this pivot point, it is going in an anti-clockwise direction. Same with this, this force over here, the force of the bridge, okay? So I've written that down here. Got the clockwise torques, which is support force A, and then we've got our 2 anti-clockwise torques, which is the torque of the bridge and the torque of the rider. So they're turning in an anti-clockwise direction around pivot point B. So I'll have to add those up eventually. Okay, so remember to calculate torques, it's force times the distance away from the pivot point. So as you can see, for support force A, I've got the unknown force, which is what we're having to figure out, okay, times the distance away from the pivot point. As you can see here, this arrow shows that the distance of support force A from the pivot point B is 4 meters. Okay, so we've done the clockwise torques as much as possible. Now we have our anti-clockwise torques to figure out. So we've got the torque of the bridge, which is its force times the distance away from the pivot point, and we can see that is 2 meters, because half of 4 meters, which is where the center of mass is 2, okay? Then we've got to work out the torque of the rider. So the torque of the rider is the rider's force, which is what we've figured out here, times the distance away from the pivot point B, which is shown by this length over here. So simplifying this side, I've got the torque force of the bridge, which is this, plus the torque force of the rider, which is this. Plussing those together, I simplify it further to get 16219. And then now I can rearrange to find what the support force A is. Okay, so how do I rearrange? Well, I want the support force A all by itself, so I have to get rid of the 4.0. Currently it's being times by 4.0. The opposite of times 4.0 is divide by 4.0. And if I do it on this side, it cancels it out here. And then I have to divide the other side by 4.0. So 1621.9 divided by 4.0 equals 4,054.75. What am I missing here? I'm missing units. Okay. So I've worked out what support force A is, which is 4054.75. What? Bananas? No. Newtons. And then I've got support force B. All right. So how do I work out support force B? Well, I could do the exact same, except make support force A my new pivot point, but I'm going to do it a different way. So feel free to do it the other way, but I'm going to do it in a different way, and you'll see how. So I'm going to use my second principle over here, that all the forces upwards must be equal to the forces downwards. And so what are my upward forces? My upward forces are support force B and support force A. What are my downward forces? I've got my bridge force downwards, and I've got my rider's force downwards. So I'm going to plug that on this side of the equation. Okay, so plugging in the values, let's do it. So support force A we just calculated to be 4054.75. I don't know my support force B. That's what I'll have to rearrange to figure out. So my downwards forces, so my bridge force is 6860, plus the force of the rider, which I worked out to be 833, and then I rearrange. But before I do that, I want to simplify things. So let's plus these values together. I should get 7693, and then now I can rearrange. So I want support force B all by itself. So the opposite of plus 4054.75 is minus this whole thing. So if I minus it on this side, it cancels it out from this side, and I have to minus it on this side. So 7693 minus 4050.75 is going to give me the support force value of 3,642.25 newtons. Rounding that to two significant figures, I get this value here. So I have officially worked out all the forces, and that's worth an excellence. Okay. So for achieved, you should have got at least one of the torques correct. For merit, you should have done this working out, but with a bit of an error. And then excellence is doing it to perfection, as we've done here. Remember your units, team, and all the best.